Before we begin, take a moment to get comfortable. Let your arms go heavy, your breath slow. And as you listen, feel free to leave a comment sharing what time it is, where you are, and what city or village you're listening from. It's love to know. And if you'd like more quiet stories like this one, don't forget to subscribe so they gently appear when you need them most. Now, let's begin. You're lying down now, your body still, but your thoughts begin to rise. Somewhere above you, perhaps just behind your closed eyelids, stretches the sky. Not the sky you see in the day, bright with sun and movement and time, but the other sky, the quiet one, the one that appears when the world exhales and the lights go out. That sky is not black. It's not empty. It's a vault of questions, a sea of quiet. You feel it, don't you? That sense of vastness pressing gently on the roof of your mind. Not heavy, not loud, just there. It's like an open door at the end of a hallway you've never dared to walk down. The sky is ancient and full of things that do not know your name, but still reflect your wondering gaze. As a child, maybe you looked up and asked something out loud. Maybe you whispered it. Is anyone else out there? Okay, and maybe, just maybe the stars shimmered slightly in reply, as if they too had been waiting for the question. Because this is how it begins. The search for other worlds doesn't start with math or telescopes. It starts with silence, with a still body and a curious mind. With someone just like you, wondering if our planet is the only harbor in an ocean of night. And it's not. A new question, thousands of years ago, long before satellites or starlight photography, people laid beneath these same skies, trying to decode the language of the heavens. They built myths. They named constellations. They imagined gods and monsters, great wheels and celestial spheres. 'Cause when you don't know what a star is, you give it meaning. And when you don't know if you're alone, you tell stories that keep you company. But stories eventually give way to science. Curiosity sharpens into tools. Wonder becomes measurement. Still, even now, in a world of numbers and satellites, the core of the question remains unchanged. Are we the only ones? As your breath slows, you can picture the earth not as ground beneath your feet, but as a small orb suspended in ink, a fragile bead wrapped in clouds, spinning in the emptiness like dust in sunlight. And the stars, they're not just points, they're suns. Each one with the potential to cradle planets. Each one a possible home for something else. Something watching, listening, dreaming. Just like you, you are floating now in thought. Far above your bed, above the atmosphere, into a darkness that is not hostile, but full of listening. In this quiet space, you begin to notice stars are not scattered randomly. They follow patterns. They form galaxies, great spirals and clouds, drifting through space like petals in wind. And nestled in these galaxies are trillions of stars, and many, so very many, have planets. You feel the shift, don't you? That moment when the sky stops being a ceiling and becomes a field, a place to explore. There was a time, not so long ago, when the only planets we knew were in our own solar system. Curie, Venus, Earth, Keech, a sibling, each known and charted. But the idea that there were other planets circling other suns, remained a dream, a theory, a poetic hope, until it WASN, single quotes, until the late 20th century, when humanity began to look more carefully. And suddenly, what was once silence became a whisper, then a murmur, then a chorus. Astronomers began to detect slight wobbles in starlight, tiny dimmings, patterns too precise to be random, hints of shadows, moving, regular, planetary. They called them exoplanets. Exo meaning outside, planets that do not belong to our sun, planets that orbit other stars far away. And with each discovery, the question of, are we alone, became less abstract, less lonely, because every new world offered a possibility, not just for life, but for understanding, for context, for a kind of cosmic companionship. Now, as you lie still, you are surrounded by known exoplanets. Test, not physically, but mentally. Thousands have been confirmed. Thousands more suspected. And that number grows with every year, like a map slowly filling in. Some are small, rocky, warm enough maybe for water to flow. Others are giants, swirling gas, worlds larger than Jupiter. Some orbit tightly, hugging their stars. There's drift, wide and slow, circling cold suns. They are real, and they are waiting. Still, even with all we've learned, the question remains. You breathe in, you breathe out. You think of all the things we still don't know. What is it like on the surface of a distant Earth-sized world? Would the sky be red or violet? Would gravity feel like a hug or a burden? Would it have oceans, winds, raindrops that carry alien scents? Would someone be standing there right now, looking up and wondering about you? The question becomes more than scientific. It becomes poetic, existential, personal, because to wonder if we're alone is to wonder what we are. If we are rare, then perhaps we're precious. If we are not, then perhaps we are part of something greater. The silence of the cosmos is not a denial. It's an invitation to ask, to seek, to dream. And so we do. We build telescopes, not just to observe, but to listen. We launch satellites, not just to study, but to search. The sky is no longer distant. It is data, it is dialogue, and even if no one answers, even if we never find a signal, never see a city light flicker on a faraway world, the very act of wondering connects us to the stars, to each other, to possibility. You close your eyes, but your mind remains open, adrift in the question, because all great discoveries begin this way, not with answers, but with silence, not with certainty, but with awe and now. As your thoughts begin to settle, you feel the questions settle with you, not as a weight, but as a companion. Are we alone? You don't need the answer yet. You only need the journey, the sky, the one that waits behind the clouds. Behind the daylight has only just begun to reveal itself. So gently, softly, your curiosity drifts forward into the next thought, the next idea, the next quiet wonder. What exactly is an exoplanet? You left off last night, or perhaps only a moment ago, floating in a question, not quite asleep, not fully awake, somewhere in that gentle velvet space between thought and dream. Do you remember the stars? The question, the sense that above you and around you was not just a sky, but a field of possibilities. Now we turn softly toward an answer. Not a final one, not a loud one, but the kind that feels like a small light in a vast hallway. What is an exoplanet? It sounds like a word from science fiction, futuristic, cold, but it's not. It's just a word for something very real. It's very far and very quietly revolutionary. An exoplanet, also called an extrasolar planet, is simply this: a planet that orbits a star beyond our sun. That's it. Not so mysterious when you say it plainly, not so difficult to define, but like many simple truths in science, this one opens 1,000 doors. Because if stars are suns, and we now know that many of them are, and if planets orbit these suns, then we must ask, what are those planets like? Are they like Earth? Are they like Jupiter? Are they like nothing we've ever imagined? The universe does not repeat itself. It does not mass produce. Each star is unique. Each planet is too. So, when we speak of exoplanets, we're not just speaking of places. We're speaking of possibilities. Now, close your eyes. Picture a star in your mind. Not our sun, another one. Maybe redder, maybe dimmer, maybe it flickers, maybe it pulses. Now, imagine something circling it, invisible at first, only guessed by its shadow. It tugs on the star ever so slightly. It dims its light just a touch as it passes in front. leaves clues in the data. This is how we first saw them. Not with our eyes, but with instruments that could read light more precisely than any eye could. These methods have names: the radial velocity method, the transit method, the gravitational microlensing method. Each one a way of detecting the unseen. Each one an extension of human curiosity. In 1992, we found the first confirmed exoplanets. They orbited a pulsar, a type of neutron star left behind after a supernova, a strange place to find planets. But they were there. Then, in 1995, the first exoplanet was discovered orbiting a sun-like star, 51 Pegasi b. It was a giant, a hot Jupiter, unimaginably close to its star. It was unlike anything we had expected, and that was the beginning of surprise, because the more we looked, the more we found planets that didn't match our expectations. There were Jupiters that hugged their stars. There were Neptunes that floated alone. There were super-Earths, planets larger than Earth but smaller than Neptune, a type we don't even have in our own solar system. Some exoplanets take only days to complete an orbit. Some take years. Some might not orbit a star at all, free-floating in the dark, cast out from their systems. It turns out that Earth's structure, its balance of land and sea, its breathable air, its moderate orbit is not universal. It may not even be common, and yet that doesn't make us special. It makes us part of a much larger family of worlds. You may be picturing them now. It's a deep blue planet circling a white-hot star. It's a planet with glowing storms, its atmosphere swirling in colors unknown to Earth. A frozen world where the wind carves canyons of ice. A water world, nothing but ocean from pole to pole. Each one real or possible, soon to be discovered. They orbit red dwarfs, yellow stars, binaries. Some are tightly locked with one face forever in daylight, and the other cloaked in eternal night. Some spin fast, some spin slow. Some of these worlds may have moons. Some of those moons may have atmospheres, and some of those atmospheres may hold traces of something more. This is why we study them. It's not just to count them, but to understand them. And not just to understand them, but to know what Earth is not. You see, when Earth was all we had, it was easy to assume it was normal. But now, with every new exoplanet, we see how unusual, how precarious, how finely tuned our home might be. Some planets are too close to their stars, too hot. Their atmospheres boiled away, leaving only rocky husks. Others are too far, frozen, silent. Their heat seeped away long ago. But in between, a gentle band called the habitable zone. Things are just right. Not too hot, not too cold. This is where we think liquid water might exist, and where life perhaps might begin. We call it the Goldilocks zone. Here, every time we find a planet in it, our pulse quickens. We wonder, we calculate, we hope, but water is not enough. Life needs more than warmth. It needs chemistry, needs stability, needs time. So we look for signs of atmospheres, of clouds, of carbon, of oxygen, of methane. We scan the starlight as it passes through these atmospheres, reading its fingerprints. We don't see aliens. We don't see cities. We don't see signs. But we do see hints. And hints lead to more. This is where the next chapters of our story begin, with exoplanets not just as places, but as laboratories. As stories, they teach us how planets form, how they change, how they survive or die. They help us see our own future, our own past. Every exoplanet is like a mirror, not showing our reflection, but showing who we could be. And that's why this question, what is an exoplanet, is so much more than a definition. It is a reminder that we are not at the center, that the universe is not small. Earth is not alone. You are drifting now, still listening, still wondering. You remember the word exo outside, beyond. It is a prefix that invites movement. It tells you that the story is bigger than the room you're in, that the stars are not background, they are destinations. And as your thoughts begin to dissolve into sleep, you hold this idea gently in your mind that a planet is not always visible, that a world can exist in silence, but not what we cannot yet see, still be out there, waiting, orbiting, listening. And as the data piles up and our tools sharpen, we move from what is an exoplanet to something even more compelling. How many of them could hold life? You're not dreaming yet, but your mind is quiet, still, somewhere between day and night, between knowing and wondering. In this soft space, we return to the stars, not to observe them directly, but to study the way they flicker. Not all planets can be seen. In fact, almost none of them are. The vast majority of exoplanets discovered so far were not found by gazing through a telescope and catching a glimpse of a tiny sphere against the void. They were found by noticing a blink, a hesitation in light, a whisper of shadow in the glowing breath of a star. This is the transit method, one of the most powerful tools in modern astronomy. And, like all powerful things, it begins in silence. Imagine a star many light years away, okay? To your eyes, it seems steady, constant. But to an observatory trained in patience, that starlight tells a story. It pulses, gently, washes across sensors. Then, one day, for a few hours only, it dims. It's just a fraction of a percent. It's not enough for you or me to notice, but enough. A planet has passed in front of it. Not in front of you, but in front of its own star. A perfect little eclipse. This event is called a transit. It's the blink that reveals a world. For a planet to transit, it must orbit its star in just the right plane edge on, so that from our vantage point, it crosses in front of its host star like a tiny shadow puppet. Most planets don't do this. Their orbits tilt away from us. They remain forever hidden. But those that do transit, they tell us far more than just I exist, because as they block a sliver of starlight, they leave a signature. And scientists have learned to read those signatures like notes in a cosmic diary. The Kepler Space Telescope was built for this kind of reading. Its launch in 2009, it stared at a single patch of sky, less than 1% of the total sky, and watched over 150,000 stars, waiting for blinks. And oh, how they blinked. Kepler found thousands of exoplanets, all by watching stars dim ever so slightly, and then brighten again. One blink might be a fluke. Blinks spaced perfectly apart suggest an orbit. K, a confirmation. A world has been found, not seen, not photographed, but discovered nonetheless. Now, breathe slowly, in, out. Let yourself imagine this strange kind of seeing. No image, no colors, just light levels. Numbers.a star dims by 0.01%. That could mean a planet the size of Earth. A dimming of 1%. That might be a hot Jupiter, a gas giant orbiting close to its star. From that dimming alone, we can estimate the planet's size, because the more light it blocks, the bigger it must be. If the transit repeats every few days, we know the orbital period. And with that, we can infer its distance from the star. Using the star's type and brightness, we estimate its temperature, and thus the planet's likely climate. A single blink, properly interpreted, tells us the story of a world we cannot see. Sometimes, during a transit, light from the star passes through the planet's atmosphere. If it has one, the gases there absorb certain wavelengths of light, leaving faint fingerprints. This is how we know that some exoplanets have water vapor, or sodium, or methane. It is astounding, this art of learning about faraway worlds, by the way they make a star flicker for a moment, like seeing a bird only by its shadow. But knowing the species, the wingspan, the color of its feathers, all from the way the sun dims when it flies past. This is science as poetry, and poetry as science. But the transit method is not without challenges. The alignment must be just right. If the orbit tilts even a few degrees, the planet will never pass in front of the star from our view, and the blink will never come. We suspect that for every transiting planet we detect, dozens more remain hidden, their shadows never falling on our instruments. That's why the number of known exoplanets, currently over 5,000, is likely a tiny fraction of what's truly out there. Somewhere on the far side of the galaxy, a planet is orbiting its star. It transits regularly every 38 days. Each time it causes a dip in starlight, but we're not watching that star. Not yet, and so the blink is missed. The story stays untold. You feel the stillness of that idea. So many worlds, unnoticed, unseen, not because they don't exist, but because our eyes haven't turned that way. That's what makes this method so beautiful and so fragile. It demands patience, stability. Time. Kepler observed its stars for years. And even then, some planets orbit so slowly that only one transit was ever seen. Just one blink. Was it a real planet or a cosmic coincidence? We wait for the second blink. Sometimes it comes, sometimes not, but we keep watching. New missions now continue to work. SAS, the Transiting Exoplanet Survey Satellite, scans nearly the entire sky, looking for brighter stars, closer planets, better candidates. It's faster than Kepler, more ambitious, and it is finding them. Planets small and large, close and far, round quiet stars and around suns that flare like fireworks. Each blink brings more questions. Each answer leads to more wonder. And soon, the James Webb Space Telescope joins the story. Not to find new blinks, but to read them in more detail, to look at those faint fingerprints in the light, and tell us what gases swirl in alien skies. Imagine it, a telescope 1,000,000 miles from Earth, watching the light of a star dim, then studying the chemistry of a world from the faintest shimmer of that shadow. That's the level of precision we now possess. And it's only the beginning, because as you listen and your breath slows, you begin to understand. Every blink is a possibility. Every dimming light is a whisper from a distant orbit, a reminder that the universe is not still, but full of motion, full of worlds. And even when we cannot see them directly, we can feel their presence in the way they bend light, in the way they pull on stars, in the way they shift our expectations. The blink that reveals a world is a lesson in humility. We are not at the center. We are not the norm. We are simply watching from our small corner as the cosmos continues to speak in pulses and patterns. And as you drift into the folds of rest, you might imagine this: a sky full of stars, each one pulsing with potential, each one waiting. And somewhere, a telescope is watching. A star dims, just a touch, and with that blink, a new world is born into our awareness. You're resting now, wrapped in warmth, held by silence, and somewhere far away, light is shifting, not in bursts or beams, but in a rhythm too small for your eye to see. A rhythm of wobble. In this part of the story, we're not watching the planet, we're watching the star, and we're noticing that even something as vast as the sun can tremble. This is the radial velocity method. It's also called the Doppler method, and it was the very first technique that let us know a planet outside our solar system truly existed, not by direct sight, but by listening to the way a star moves, gently, back and forth, like a swing suspended in the dark. Here's the idea. A planet orbits a star. Yes, but gravity works both ways. The planet pulls on the star, just as the star pulls on the planet. Even though the star is much heavier, it still reacts. It moves. A little, a slow dance, a subtle wobble. And that wobble can be seen not in images, but in color. Let's return to something familiar. Sound. When an ambulance passes you, its siren changes pitch. Higher as it comes towards you. K. Lower as it moves away. That's D. Doppler effect. And light behaves the same way. When a star moves towards you, its light shifts slightly toward blue. When it moves away, the light stretches toward red dot. Astronomers can measure that. They look at the spectrum of starlight, the rainbow broken into lines, each marking a known element. Hydrogen, helium, calcium. If the lines shift a little to the red, the star is moving away. If they shift to the blue, the star is coming closer. Now imagine those shifts happening over and over again in a pattern, on a cycle that tells us the star is not moving away permanently, nor coming toward us for good, but instead wobbling, swaying gently as if being tugged back and forth by something unseen. A planet, orbiting, pulling, whispering its presence through the trembling of its sun. This is how we found 51 Pegasi b. In 1995, the first confirmed exoplanet around a sun-like star. We didn't see the planet. We saw the stars wobble. We measured the cycle. We saw it sway, and we realized there's something massive. It's very close in, pulling hard. That something was a hot Jupiter, a gas giant orbiting its star every 4 days. So close it blisters, so heavy it makes the star dance. Since then, we found hundreds more using the same method, especially the giants, especially the loud ones, those that tug and wobble and shout through their gravity. But the precision has improved. Today, with better instruments, we can detect the wobble caused by a planet just a few times the mass of Earth. Sometimes the star shifts by only a few meters per second. Walking pace, just a gentle step, but we see it, and we know a planet is there. And again, just like with transits, we can learn more than yes or no. From the amplitude of the wobble, we estimate the mass of the planet. The bigger the wobble, the heavier the companion. From the frequency, we learn the orbital period. And from that, we calculate the distance from the star. We don't just detect planets. We begin to map them, sketch the invisible based on motion we can measure. And just like before, you breathe deeper now, noticing how the universe tells its secrets without words, without images, just with movement. Quiet, consistent, revealing. But there's more, because not all orbits are circular. Some are elongated, stretched like ovals. That too leaves a fingerprint in the timing of the star's wobble. A smooth wobble, circular orbit, a sharp change, elliptical. We read the curve like handwriting. And then there's multi-planet systems, stars pulled not by one, but by several companions. Their wobbles layer on top of each other, overlapping, interfering, dancing, and from that complexity, we pull out patterns. One planet here, another there. K, tugging from afar, all inferred from motion, from a wobble you could never see without. Light spread thin into color and watched for years. This is science as interpretation. Not guesswork, but artful precision. You might wonder, how sensitive must our instruments be to detect a wobble of a few meters per second on a star dozens of light years away? The answer is extraordinary. Telescopes like HARPS in Chile, an espresso on the Very Large Telescope, can detect shifts in velocity as small as a human walking slowly across a room. Think about that. From Earth, we can see a star 40 light years away move at the speed of a toddler's crawl because a planet is pulling on it. That's how fine-tuned our listening has become. We cannot yet see most of these planets, but we can feel their presence through gravity, through motion, through wobbles. And this has changed the way we understand stars. They are not alone. They are not fixed points. They are dancers, responding to partners we can barely perceive. Some walk slowly with distant giants. Others jitter with close-in super-Earths. Some move with barely a tremor, while others twist and twist again, tugged by several invisible hands. And slowly, from the symphony of motion, we are building a map of the galaxy, a map of companions, a census of worlds, many stars, it turns out, host planets. Perhaps most do. The wobble reveals them one by one, and yet you wonder, what else moves, unseen? What else trembles, just outside perception? On Earth, you sense the people near you. By the way, they shift the air. You feel when someone walks past, when a breeze lifts a curtain, when a presence enters the room. Stars feel their planets that way, and we, listening across light years, read that sensation from a stream of light. That is never still. A kind of empathy spread across space. You're floating now, drifting into that idea that perhaps all of us, stars and planets, people and thoughts, move each other, even if only slightly, even if only by wobble. And maybe we are all detectable to someone if they watch us long enough. So rest with that. You are not a fixed point. You, too, have a rhythm, a movement, a signal, and the sky, ever trembling, reminds us that everything beautiful leaves a trace, even in the wobble of a distant sun. You're floating now, warm, still, safe in the velvet dark of thought, and across the vast silence of space, planet orbits a star, not too close, not too far, a distance that isn't random, but balanced. It is in the habitable zone, the Goldilocks zone, the place where liquid water might survive. You remember the story. Goldilocks tried 3 bowls of porridge. One was too hot, one was too cold, one was just right. In the same way, planets around stars can be too scorched, or too frozen, or just right for life as we understand it. That just right is not a guarantee. It's a possibility, a question, thread to follow. It begins with warmth, star's warmth, not too intense, like a furnace of radiation that evaporates oceans before they can form. Not too faint, like a flickering ember that leaves the ground, buried in eternal frost, but something in between, something gentle, sustained, enough to keep water in its liquid state. Water, simple, universal, 3 atoms. And yet, the foundation for all life we know. We're made of it. We evolved in it. We carry it in our blood, our breath, our cells. So when we search for life beyond Earth, we search for water. And where water can be liquid, life, maybe, can begin. That's the purpose of the Goldilocks zone. Not a destination, but a filter, a clue, a place where Earth-like conditions might happen again. But it's delicate. The size of this zone depends on the star. For a sun-like star, the habitable zone might stretch from about 0.95 to 1.4 astronomical units. And O is the distance from Earth to the Sun. Earth sits at 1 astronomical unit, just right. Venus is closer in 2. Hot Mars is farther out, too cold, but stars vary. A red dwarf, cooler and dimmer, has its habitable zone much closer in, maybe just 0.1 astronomical units, closer than Mercury is to our Sun. A hot, blue giant would push its habitable zone far away, but also live fast and die young, giving little time for life to emerge. So the Goldilocks zone is not one size fits all. Ups, shifting ring, living zone, tied to the heartbeat of a star. And even being in that zone doesn't guarantee anything. A planet might be in the zone, but have no atmosphere, or too thick an atmosphere, or no magnetic field to protect it. Or a surface of toxic rock and acid clouds. Venus is a lesson in that. It sits just at the edge of the habitable zone, but is anything but hospitable. Its atmosphere is thick with carbon dioxide. Its surface hot enough to melt lead. Its clouds are sulfuric acid. So being just right on paper is not always just right in practice. And yet, it is a start. It is hope, a place to aim telescopes, a zone to monitor, a location where the conditions for liquid water, and by extension, life, are possible. In 2015, astronomers found Kepler-4 to be a planet in the habitable zone of a star, much like our Sun. It's about 1,400 light-years away, larger than Earth, but orbiting at just about 1 astronomical unit. A planet that could be rocky, that could have water, that could perhaps be home. And there's TRAPPIST-1, red dwarf, just 40 light-years away, with 7 rocky planets. At least 3 are in the star's habitable zone, 7 worlds. 1 tiny star, and at least 3 just right. They are not Earth. They may be nothing like Earth, but they sit in the zone, and we listen. Because what if? What if water flows quietly on their surface? What if clouds drift across their skies? What if rain falls in pools and carves tiny rivers into alien rock? And then the deeper question, what if something drinks it? What if something stirs? You drift further now, held by the rhythm of thought, held by gravity, held by light, and the Goldilocks zone drifts past like a ring around every star. Band of maybe, a perhaps, a quiet promise written in distance and warmth. But there's more. Because Earth hasn't always stayed just right. The sun has grown warmer over time. The habitable zone has shifted outward, and yet Earth has stayed temperate. Why? It's thanks to a balance, a dance between greenhouse gases, volcanoes, oceans, and even life itself. Earth regulates, it breathes, it adjusts, a delicate thermostat, one that keeps conditions within a livable range for billions of years. So a true habitable planet must not only be in the right zone, it must be able to stay there, to adapt, to respond, to maintain equilibrium across deep time. This is the challenge and the wonder, because some planets might have been habitable once, but are now barren. Others might be frozen now, but warming slowly into possibility. The habitable zone moves. Time matters. It's not just about where a planet is, but when and even how, because a thick atmosphere can make a farther out planet warmer. A reflective surface can keep a closer in planet cooler. The math is complex, but the goal is simple, to find a place where oceans can form and remain. And in those oceans may be life, not guaranteed, not even likely, but possible. A quiet whisper of hope in the silence between stars, and you lie still, letting the concept settle around you like mist on cool grass. There are billions of stars in our galaxy, each with a zone of maybe, a place that could be warm, stable, right? How many have planets? Most. How many of those are rocky? Many. How many orbit in the zone? Thousands. Tens of thousands. Caps more. How many have water? How many have life? Feel the question pass over you like a breeze. It's no answer. Just the calm of asking. Just the joy of wondering. You are one life on one world, orbiting one star in one Goldilocks zone. That happens by cosmic chance, to be just right. And out there, somewhere, another world may be spinning, clouds drifting, light warming soil, water tracing its path down a hillside of alien stone. Not too hot, not too cold, just right. You've been drifting through the dark, following light, following motion, following water. Now you drift again, but toward something that feels familiar. You don't know why, you've never seen it, but still it feels like home. They are not Earth, but they echo it, Earth's shadow sisters. That's what some call them. Rocky, quiet, tethered to stars that shine not like ours, but still enough to warm their skin. They orbit, not in fantasy, but in cold math. In telescope glimmers, in transit shadows. We haven't touched them. We felt them. And when we speak of Earth-like planets, we do not mean twins. We mean reminders, echoes, possibilities. You close your eyes and imagine one now. A planet not unlike Earth, perhaps the same size, or just a little larger. Its gravity only slightly heavier, enough to make your steps feel thoughtful. enough to press your heartbeat down a little closer to the ground. Its surface, rocky, solid beneath the feet. Perhaps mountains, perhaps plains, perhaps a sea that hugs the curvature of its horizon. It orbits a red dwarf, the most common kind of star in the galaxy. It's cooler than our sun, smaller, but it burns with longevity, billions of years beyond what our sun will ever see. And because it's cooler, the planet must orbit close to stay warm, tightly, like a marble spun right next to a flame, so close that it may be tightly locked, one side always facing the star, the other in perpetual darkness. You imagine standing on the Terminator line, the edge between day and night, where light slips across the horizon like a knife, and the wind stirs endlessly from hot to cold. It could be there, right at that in-between that life holds on, not on the day side, scorched, not on the night side, frozen, but in the gray, twilight in between, a narrow band of maybe, and you wonder if something lives there. Does it sleep? Does it have a word for dawn if there is never a sunrise? You float now to another sister. It's one larger, a super-Earth, maybe 1.6 times Earth's radius. It's twice the mass, heavy, more atmosphere. Maybe thick clouds swirl over it like bruised cotton. Maybe it rains with strange chemistry. Maybe the pressure hugs every surface like a second skin, but still rock beneath. Maybe volcanoes, maybe rivers of molten rock or liquid water trapped beneath glacial crusts. There's LHS 1140. B, a real world, a real shadow sister. It's 1.4 times Earth's size, discovered in 2017, orbiting a small, cool red dwarf just 40 light years away, in the habitable zone, with signs of an atmosphere. It's possibly dense, possibly stable, possibly hiding oceans. We haven't seen its shores, but we can model its skies. And then there's Proxima Centauri b, the nearest known exoplanet to Earth, just over 4 light years away, orbiting the red dwarf Proxima Centauri, our sun's closest stellar neighbor. It's roughly Earth-sized, and it lives in its star's habitable zone. But there are questions. Proxima flares violently. Its light is not gentle. Could an atmosphere survive that? Could life conceal the fact that it exists so close stirs something inside? You think of all the stars you've ever seen. How many of them might have shadow sisters? Like doesn't mean comfortable. It doesn't mean safe. It means familiar enough to imagine. And sometimes it's all we need, because every exoplanet has a story and a setting. Some have thick hydrogen blankets that trap heat and turn oceans into steam. Some orbit 2 suns, a sky of double shadows and double sunsets. Some are covered in ice, but may hide warm oceans underneath, where hydrothermal vents breathe heat into the dark. There could be forests or fungus, or nothing at all. Some might be silent. Some might be singing, but we don't yet know the tune. And then there's the matter of atmosphere, because it is not enough to orbit in the habitable zone, to be rocky, to be quiet. You must also breathe, not like us, but with chemistry, interaction. We search exoplanet atmospheres for signs of balance, of gases that shouldn't be there together unless something keeps adding them. Oxygen and methane, for example, both can destroy each other. So if they're both present, maybe something is replenishing them, maybe life. And so we read the fingerprints of light as it passes through alien skies, looking for water vapor, ozone, carbon dioxide, and hope. It is a slow reading, a patient art, but sometimes we catch a hint, a molecule, a shadow, a whisper of a possible breath. These Earth-like worlds, they aren't rare. That's the quiet. Wonder.Kepler and TESS, our planet hunting telescopes, have shown us that billions of such planets likely exist just in our galaxy. Billions. Many are yet undiscovered. Most are unnamed, but they are there, waiting, orbiting, holding their stories behind veils of distance and time. And as you lie there, imagining distant shores, you wonder if you stood on one of these planets and looked up, would the sky feel familiar? Would the stars trace patterns you'd recognize? Would you feel alone or just far from home? Maybe gravity would hug you more tightly. Maybe the air would taste like minerals you don't know. Maybe the wind would carry strange scents from forests that never knew Earth. But maybe, just maybe, you'd recognize the feeling of solid ground, of warmth, of looking up and wondering. Earth's shadow sisters don't need to be identical. They only need to remind us that the conditions of life are not unique, that nature repeats itself by given the right elements in time and distance. Something like Earth can happen again, and perhaps again, can't again. Some will be lifeless, but some may be living. We won't know until we go, or until the light tells us a secret we've never heard before. And so we listen, we model, we send telescopes like JWST and Ariel to pierce the atmospheres of these distant worlds with light. We imagine them, we name them, we map their orbits and catalog their stars, and still we wait, because to explore them is to step outside of it. Earth, not just physically, but emotionally. It is to believe that we are not the only melody this universe can sing, that perhaps on a rock the size of Earth, orbiting a star long and dim, there are rivers and clouds and something breathing, maybe not like us, maybe never like us, but still alive. You lie back now, it's held by starlight and questions, wrapped in soft, dark thought, and in your mind, a rocky planet orbits quietly. Its sun is not ours, sky is not ours, but it turns day after day, shadow after shadow, held in balance, waiting, not too hot, not too cold, just a little distant, just a little silent, a sister. You're floating now, quietly, beyond the familiar rocky orbs and just right zones. The light grows stronger, not from nearness, but from something unnatural, a planet that glows not by reflection, but by sheer heat. It hums like a coiled ember, smoldering beside its star, never far enough to cool, never close enough to vanish. You've met Earth's shadow sisters. Now, meet the opposite, the extremes, the giants too close to their flame. Hot, JUPITERS, tot planets, so massive, so bloated with gas and heat, that they orbit their stars in days, not years. Imagine that. A planet larger than Jupiter, yet it circles its sun faster than our moon circles. Earth tidal forces stretch it. Solar winds burn it. Still it turns. A year on some hot Jupiters lasts just 1.5 Earth days. A full orbit, sunrise to sunrise. In less than a weekend, take 51 Pegasi b, the first exoplanet ever discovered, orbiting a sun-like star dot in the year 1995. It defied everything we thought we knew. Here was a gas giant, bigger than anything in our inner solar system, orbiting closer than Mercury. It wasn't supposed to be there. Planets like that, we thought, belonged farther out in cold, wide orbits, like Jupiter or Saturn. But 51 Pegasi b changed the rules, and once we saw it, we saw hundreds more. Hot Jupiters became a whole new category. Not rare, just unexpected. They are enormous, often 1 to 2 times the mass of Jupiter, but bloated, puffed up by their heat, like gas balloons inside a furnace. Their atmospheres expand, their outer layers drift away. Some leave trails, long comet-like tails of hydrogen being stripped away by how close they orbit their stars. And that star, to them, it is everything. Imagine standing in the upper cloud deck of a hot Jupiter, if that were even possible. The sky would be a dome of fire. No night, no darkness. It's just endless day and the roar of solar wind. On the day side, temperatures rise above 2,000 degrees Celsius or 3,600 degrees Fahrenheit. Metals turn into vapor. Iron falls like rain. Glass forms in clouds, then falls sideways in 5,000-mile-per-hour winds. A storm that circles the planet forever. It's trying to move heat from the day side to the night, but never fast enough to cool it. The night side, if it exists, offers no rest. Some hot Jupiters are tightly locked, with one side always facing the star, the other forever in shadow. But others spin quickly, their winds throwing heat around in wild storms no Earth eye has ever seen. And beneath those clouds, we do not know. There is no solid ground. It's only pressure, density, and layers upon layers of gas that become metal like hydrogen. Deeper down, a place where magnetism rules, where lightning dances, magnetic fields stretch across space, and yet some of them are beautiful, like WASP 121, be a planet so close to its star. It's stretched into the shape of a teardrop by gravity. Its atmosphere escapes into space, glowing with vaporized metals. We've seen iron, magnesium, something called vanadium oxide in its skies. Some planets are more intense still. Kelt 9b, for example, orbits a blue star so hot that the planet's temperature reaches over 4,300 degrees Celsius. That's 7,800 degrees Fahrenheit, hotter than some stars. Its air isn't just hot, it's plasma, it's atoms broken into pieces. A planet's sky turned into energy. It circles its star in just 36 hours, a year and a lifetime, again and again in less than 2 days. And so, these giants, Ks, these burning wanderers, exist at the edge of what we thought was possible. But how did they get so close? That's one of the quiet questions, because if planets form far from their stars, in cold, dusty disks, as we believe, then hot Jupiters must have moved inward over time. They didn't begin this way. They traveled, they migrated. Imagine a massive planet drifting inward through gas, dust, and smaller bodies, clearing everything in its path. Some call it planetary migration, others call it orbital decay, and along its journey, destruction, chaos, or a new kind of order. These giants can break the orbits of smaller planets. They can throw rocky worlds into space, or push them into their star, or they can settle into a tight, burning orbit, like a moth circling a flame forever, just out of reach. Some scientists think that's why many systems with hot Jupiters have no small, inner rocky planets. They may have been destroyed when the giant passed by, a cosmic crash, unseen but noticed in the silence where a world should have been. And so hot Jupiters may not only be strange, they might be dangerous too. Or maybe just survivors of a violent past. And yet, some may even help. In a few systems, the presence of a hot Jupiter may have made other orbits more stable, giving other planets a chance to survive. There are even hot Neptunes, warm sub-Saturns, a whole group of huge, unexpected planets. They tell us that our solar system isn't the model, just one version, and in a universe this large, surprise is normal. You float now past one of these scorched giants. It turns slowly. Its clouds burn orange. Its magnetic field crackles like a quiet storm, and still it feels peaceful. It's in its own strange way, predictable, constant, a furnace that dances around its sun with perfect rhythm. Its storms rage, but they've done so for ages. Its orbit is deadly, but stable, and it teaches us something powerful. Not all planets are safe. Not all are like Earth, but all are part of the same story. And sometimes, the loudest voices in space are the ones we hear first. That's why hot Jupiters were the first exoplanets we discovered. Their huge mass and tight orbit pull on their stars, causing a wobble we can detect from Earth. Their constant transits make them flicker like flashing signals in telescope data. They were first because they made the most noise. They shouted through space, and we listened. And now we search for the quiet ones, for Earth-like planets. But we remember the giants who called us first. They are not homes, not havens, but they are messages, clues, and they remind us the universe wasn't built for comfort, it was built for wonder. You float again, quiet as dust, hovering just above a planet you can never touch. There's no shuttle to land, no probe to walk, no drill, no scoop, no sample to return. This is not geology. This is not boots in soil. And yet, you will know what this sky contains. You will sniff its clouds and read its vapors from hundreds of light years away. Because in astronomy, light is more than brightness. It is language. It is texture. It's taste. And today, you are tasting water on a planet you cannot touch. It begins with spectroscopy, a word that sounds hard, but means something gentle. It means to split the light, like rain splitting sunlight to a rainbow, except instead of 7 colors, you find thousands. A detailed barcode, a fingerprint of atoms. Each element absorbs and emits at its own precise wavelength. Hydrogen sings in one key, sodium in another. Water vapor, song with deep notes and soft harmonies. When light from a star passes through a planet's atmosphere, even for a moment, that light carries the flavor of the gas it passed through. You cannot see the planet, but you can see the light. You cannot touch the clouds, but you can read the silence between wavelengths. There are 2 ways to taste an alien sky. One is during a transit, when a planet passes in front of its star. As it does, a tiny sliver of starlight filters through the edge of the atmosphere. The light bends. It travels through haze, through gas, through molecules dancing in heat and height. That altered light reaches your telescope, and you split it, like glass splits sunlight, finer, deeper. You compare it to starlight before the transit. Subtract what is missing, and what's missing tells you what was there. Water vapor, carbon dioxide, methane, even exotic compounds like titanium oxide. And with those molecules, the story begins. The other way is an emission. When a planet passes behind its star, a secondary eclipse, you see a drop in total light. You've lost the planet's own thermal emission, however faint. Subtract again. Analyze what was there before and after, and in that faint glow, you can read a planet's own heat signature, its own atmospheric fingerprint. It's not perfect, it's faint, it's difficult, but it is real, and it is enough to know whether a planet has an atmosphere, whether it reflects or absorbs, whether it glows with trapped heat or cools quickly in its orbit. This is how we know that some exoplanets have clouds made of salt, others iron or sand or silicates. One, we suspect, rains liquid glass. Another has clouds made of titanium vapor, metal turned into mist, and in a few, we have tasted water vapor, not oceans, it's not lakes, but the mere presence of water molecules suspended in an alien. Sky tells us this planet is not dry, and where there's water, there may be habitability. Not certainty, but hope. Take HAT P11b, a Neptune-sized planet 124 light-years away. Using the Hubble and Spitzer space telescopes, astronomers detected water vapor in its atmosphere, not oceans, but clouds, steam, signals of structure, a hint that this distant world, though harsh and alien, has weather, decay, and change, and movement, a living atmosphere, not a dead envelope of gas. Even more tantalizing, K218b, a super-Earth, a rocky planet, or perhaps an icy one, orbiting a red dwarf within the habitable zone, and it has water vapor. The first habitable zone planet, where we've seen this sign. Its skies are thick, perhaps too thick. Its pressure may be crushing, its clouds eternal, but in that sky drift molecules of HO, and if water floats there, what else might? Bacteria, chemistry, or only the memory of possibility? We do not know, but we know to look. You listen to alien atmospheres, not with ears, but with light. And the instruments that read this light are delicate. James Webb Space Telescope, with its golden eye, sees in infrared, where heat speaks softly. It sees more detail than Hubble ever could. Already, it has confirmed water on exoplanets like WASP-96b. It has seen haze, clouds, the structure of atmospheres in worlds we can never touch. And someday, it may see BIOSIGNA2 or ES, words in the light that say, I am alive. But what are we looking for? What would a living atmosphere look like? On Earth, our sky is shaped by life. Plants fill it with oxygen. Animals exhale carbon dioxide. Microbes influence clouds, release methane. Life leaves a chemical imbalance in our atmosphere, one that wouldn't exist if the planet were dead. So, we look for that imbalance, the presence of oxygen alongside methane, carbon dioxide in strange quantities, a planet that's too clean or too dirty for geology alone. And though we cannot land, we can read these clues in the light. One day, perhaps, you will see a line in a spectrum and know that is life, a whisper from another world saying, I'm here. Not loudly, not clearly, but enough to lean forward, to pause, to wonder what it looks like on the ground beneath those clouds. You can't breathe that air, can't taste it, but the light tasted it for you, and that is enough. There are limitations. Spectroscopy depends on alignment. The planet must transit. The light must be strong. The atmosphere must be thick enough to read. Thin atmospheres, like Mars, they're nearly invisible. Cloud-covered planets, like Venus, they may hide everything. Sometimes the signal is lost in noise. Sometimes the light never bends our way, but other times it works, and it is beautiful. You now float not above one planet, but thousands, each orbiting a different star, each sky carrying a different signature, like a wine taster savoring hints of pepper, earth, and plum. You sip the spectrum and tell its story. This one has sodium. This one is hazy. This one has a signature of water. And one day, one of these skies will taste like earth, a signature of blue, of life, of breath. And that will be enough to know where to look next. Because you are not done looking, and the skies are not done whispering. They carry stories of gas and gravity, of sunlight and chemistry, of planets that form, wander, and wait. And if one of those planets carries something living, something breathing, then its atmosphere is the first to speak, and you will hear it in silence, in spectra, in soft dips of light and lines on a graph. That's how you find water without touching it. You let the light bring the taste to you, and you listen for the story beneath the shine. You drift now not above a planet, but in a question. A single thought floats through the dark. How do you recognize life from the other side of the stars? You cannot see its shape, cannot hear its voice, cannot hold its soil or breathe its air. You are a watcher, listening to what planets do not say out loud, but whisper through their chemistry. And so the question becomes not, is there life, but would we know it if it was staring back? Earth speaks, not with words, but with breath. The air around you, what seems ordinary, is, in truth, wildly unusual. Oxygen does not linger. It bonds, reacts, burns, and yet Earth's sky is thick with it. Why? Because something keeps putting it there. Something persistent, something alive. Trees, algae, tiny microbes humming in soil and sea. Oxygen is a byproduct of photosynthesis. Life, feeding on light, exhaling with every breath of green. And so, on Earth, life has changed the entire atmosphere. That is its fingerprint. But oxygen alone is not enough. It can be forged without life, in violent ways. UV rays, splitting molecules, heat driving reactions. What we need is an imbalance, a kind of planetary contradiction. Too much oxygen and methane, K, gases that should destroy each other but remain side by side, or trace gases in strange harmony. Carbon dioxide with nitrous oxide, ozone with ammonia. When chemistry on a planet doesn't make sense, you listen harder. Because sometimes nonsense is the sound life makes when it exhales. This is the search for biosignatures, not evidence of beings, not messages or machines, just the presence of unstable chemical patterns that suggest life is refreshing the sky. Signs that something beneath the clouds is moving, breathing, metabolizing, like seeing smoke and wondering what's on fire. Not the fire itself, but the trace it leaves in the air. You might find them in the infrared, where warm planets glowed, or in the visible spectrum, where reflected light carries hints of what it passed through. You might measure the color of a planet and notice a faint green tint, the vegetation red edge, a spike in light just beyond red caused by chlorophyll on Earth. If found elsewhere, it could mean alien forests breathe under distant suns, or something like them, or something totally different that ends up looking eerily familiar. But what counts as life? Would alien microbes even use the same chemistry? Would they breathe oxygen or exhale something else? What if they thrive in methane or swim in oceans of ammonia? What if their version of photosynthesis uses a different pigment, a different spectrum of light? We cannot assume too much. We must look for patterns, not exact matches, because life may not look like ours. But its fingerprints may still smudge the skies above. That's why astronomers build libraries of possible biosignatures, dozens of gases, ratios, pressure temperature, combinations. They run simulations of planets that never existed to ask, what would life look like if it didn't look like Earth? Could sulfur-based organisms live in dense, hazy skies? Could life emerge in a world bathed in red dwarf light? Could carbon chains and long hydrocarbon molecules build a biosphere in an ocean of methane? Every possibility is a puzzle piece, each spectrum a test, and each time you listen to a planet's sky, you compare it to these models, these silent expectations, hoping the planet says something different. Take TRAPPIST-1e, small, rocky planet in the habitable zone of a cool red star. Tantalizing, Earth-sized, temperate, a perfect candidate to scan for atmosphere, for imbalance, for fingerprints, and if oxygen or methane are ever found there, especially together, it would be a moment of deep stillness, not proof, but the closest thing to a breath heard from 1 trillion miles away. The challenge is clarity. Planets are small, stars are bright, and noise is everywhere. Biosignatures must rise above the static, must shout softly through the scatter of photons and distortion. That's why missions like the James Webb Space Telescope are so precious. They are not looking for aliens. They are listening for skies that contradict themselves, worlds whose chemistry whispers an echo of metabolic change. And soon, other missions will follow. Love War, Habex, Origins, Ariel, each telescope more sensitive, each sensor more precise. They will stare at small, rocky worlds around quiet stars and listen. Listen for carbon. Listen for nitrogen, and for the holes in the spectrum where something took a bite of light and left its shadow behind. But there's something else you must remember. Sometimes life is quiet. Sometimes it is buried. There may be planets alive below the surface, neath oceans, inside crusts where no gas escapes. A breathing world with no sky to change. We wouldn't know, and that's humbling. It reminds you, absence of evidence is not evidence of absence. So you stay patient. You keep listening, and you build better ears. One day, perhaps, a planet will rise in the data that changes everything. A sky too oxygen-rich and too methane-heavy to explain with geology. It's chemistry that only life could keep unbalanced. And then, school not have proof, but you will have something more powerful, a question that won't go away. What would it feel like to see a graph that might contain life? No image, no voice, just lines on a spectrum. Would your heart race? Would you pause? Or would you feel a quiet sense of inevitability? Of course, there's life. There always was. We just learned how to listen. And that is the magic of biosignatures. Not that they proved, but that they suggest. They take the unknowable and make it almost graspable. They whisper, "You are not alone." And though you cannot yet speak back, you know where to aim your telescope next. You know where to listen, and that is how discovery begins. Not with a shout, but with a single, careful breath from a distant world you've never touched, but have finally heard. You are listening, still UNMOVNG, not for sounds of thunder or screams across the cosmos, but for a hush to break, for a whisper, a pulse, some tiny signature of intention to drift across the stars, but nothing comes. The sky is a still lake, not even a ripple, and you wonder, not for the first time, if you are truly alone. We found thousands of planets, rocky ones, gas giants, Earth-sized, scorched, frozen, just right. We've studied their skies, we've traced their shadows, we've watched their stars wobble and dim, but they don't speak. They do not send beams of light with clever encoding. They do not pulse radio waves with structured signals. They do not shimmer in strange patterns that defy the natural. The stars stay stars. The planets stay silent, and we remain watchers, patient and unsure. In 1960, the radio telescope turned toward the star Tau Ceti. Frank Drake listened for a transmission. Anything, the silence was vast, but hope remained. We called it CTI, the search for extraterrestrial intelligence. Not a search for life, but for a mind, for intention, for something out there that wanted to be heard. Since then, we've sent our own messages. We've beamed radio waves toward star systems with coded patterns, mathematics, DNA diagrams, maps to Earth. We launched golden records into the void, Voyager 1 and 2, now leaving the solar system with human voices, music, the image of a newborn baby crying. We have tried, but the stars do not answer. There is silence, a deep, aching, quiet that feels heavier the more you know. Because in all the ways we can listen, in all the clever tools we build, we have found only the sound of our own breath in a room with no echo. And so you ask, what does it mean? Maybe it's too soon. Maybe we are the first life to reach 4 stars, to build machines, to wrap equations around gravity. Maybe the silence is the sound of a universe just waking up, and we are its early dreamers, wondering why the sky feels empty, but not forever, just early. Or maybe everyone else is too far to reach, too far to hear, too far to even know we're asking, even at the speed of light. A message from a distant galaxy would take millions of years just to arrive. And what if it was sent before we were even born? What if civilizations rise and fall while their messages drift through empty space? We would never overlap. It's only echoes from worlds already gone. Perhaps they're there, but hiding, intentionally, the dark forest theory. Each civilization is a hunter, afraid to speak, lest they be heard by something with teeth. So they stay silent, invisible, like ghosts in a house with locked doors. We might be shouting into a room where everyone else is holding their breath, not because they're not there, but because they've learned it's better not to speak. Or maybe intelligence is rare, more rare than stars, than planets, than water, or even life itself, because intelligence is not just survival, it is reflection, language, the urge to build, to destroy, to seek. Maybe it's a flicker of phase some worlds pass through before retreating back into silence. Maybe we are a brief flame in an otherwise quiet night. Still, we listen, not because we expect, but because hope is its own signal, a hum beneath the static, kind of faith that the universe, though ancient and vast, is not empty, just slow to reply. There are telescopes now, always watching, in New Mexico, in China, in Australia, on satellites above us. They collect radio waves from all directions. Thousands of stars are monitored for signals that repeat, that stand apart from natural pulses and flares. And every now and then, a signal appears, brief, sharp, mysterious, like the wow signal in 1977, a powerful burst that lasted 72 seconds and never returned. We saw it, we circled it, we pointed back, but it was gone. Maybe that was nothing, or maybe that was everything. Maybe that was a knock on the door that we missed, or maybe it was just space doing something odd. We don't know, and so we keep listening, because silence, for all its weight, is still a kind of answer, and silence changes you. It teaches you to pay attention, to slow down, to notice the tiniest blip in a sea of background noise. You become a student of static, learning to see what isn't there, because sometimes the absence is the message. Even now, there are projects looking deeper. The Breakthrough Listen initiative is scanning the sky with unparalleled precision. Billions of frequencies, thousands of stars, petabytes of data, not one confirmed signal yet. We measure silence like we measure sound. Now, each quiet star, each mute planet adds another data point to our growing map of possible company. The more we hear nothing, the better. We understand where someone might speak and what it might sound like if they do. There is comfort in the quiet. 2. If the galaxy feels empty, then perhaps we are special. Not in arrogance, but in responsibility. Perhaps we are the only voice right now in what we say, what we send, how we treat each other. It might matter in ways we can't yet imagine, because if the universe is listening and we are the first to speak, then our words carry more than just meaning. They carry memory. So maybe speak gently, softly, with awe, not knowing if anyone will hear, but hoping they will understand, because silence is not proof of emptiness. Sometimes it is just the pause before the answer. You drift now in that pause, not lost, not alone, just waiting, like a bottle on an endless sea. Your message still sealed, still dry, still floating. And maybe one day a hand will reach out and open it, and maybe then the stars will not feel so far away. You're floating now, quiet as a breath, steady as a thought that lingers above you. A sky too wide for names, and in the silence, a whisper of metal, a memory of machinery, once turned toward the stars. It did not blink, it did not rest, it simply watched, and by watching, it changed what we thought was possible. This was Kepler, a telescope named for a man who loved orbits and harmonies, who believed the heavens were legible if only one had the patience to listen. The Kepler Space Telescope was launched into silence in 2009. It carried no explosive engines, no massive mirrors, no roaring ambitions, just a gentle lens, a precise eye, and a single task: to stare at one patch of sky, to never look away. To wait, it watched the Cygnus constellation. Not the whole sky, just a sliver, a narrow triangle of stars, like a single page in a library of galaxies. And in that patch, Kepler waited for stars to dim. That's all. It waited for shadows. When a planet crosses its star, from our distant point of view, it casts a small shadow, a dimming, momentary blink in the starlight. This is the transit method, and Kepler became its most patient practitioner. Imagine staring at a single candle for weeks, for months, just to see if something tiny passed in front of it. Now multiply that by 150,000 stars. That's what Kepler did. And the blinks came, faint dips in brightness, repeating every few days or months or years. Not flashes, not fireworks, patterns, whispers. Ted Kepler didn't see the planets, it saw their effect, their trace, like the rustle of wind without the wind itself. From those flickers, scientists could guess the size of the planet, its orbit, its distance from the star. Sometimes they even guessed its temperature, its composition, its potential to host water. All from a shadow. Kepler was tireless. Over its first 4 years, it discovered over 2,300 confirmed exoplanets and identified thousands more as candidates. That's more than all the planets we had ever known before. It found hot Jupiters circling too close, super Earths in strange orbits, and multi-planet systems that looked nothing like ours. It shattered the idea that our solar system was typical. It wasn't. The cosmos was stranger, more diverse than we'd imagined. And then, something shifted. In 2013, 2 of Kepler's 4 reaction wheels failed. These were tiny gyroscopes that helped it maintain its aim with incredible stability. Without them, Kepler could no longer hold its gaze. It was like asking a painter to finish a portrait with trembling hands. But still, Kepler did not go silent. Engineers found a clever solution. They used solar pressure, the gentle push of photons from the sun itself, to balance the telescope like a tightrope walker with arms outstretched. This became the K2 mission. No longer fixed on one patch of sky, Kepler now observed smaller regions for shorter times. It was less precise, more limited, but still, it watched. Still, it listened, and it continued to find planets. Kepler's final moments came quietly. In 2018, its fuel was gone. Its ability to position itself faded. NASA let it sleep. No crash, no explosion. Just a gentle shutdown of a telescope that had spent a decade watching shadows. But Kepler's story didn't end there. Its data, terabytes of light curves and dips, wobbles and flutters, is still being studied, still parsed, still revealing. Thousands of volunteers joined citizen science projects, scanning graphs, clicking through brightness charts, helping astronomers find what machines might have missed. One planet, then another, then systems of 3, 4, 5. Kepler's silence still speaks. And what did it teach us? That planets are everywhere. Before Kepler, we wondered if other stars had planets. After Kepler, we knew not just a few, but most. Kepler taught us that our solar system isn't rare, it's normal, that there may be billions of Earth-sized planets in the Milky Way alone. It redefined our sense of scale, our assumptions about uniqueness. It made the universe feel more crowded, somehow more welcoming. Some of the most famous exoplanets come from Kepler's. Watch Kepler-186f, an Earth-sized planet in its star's habitable zone. Kepler-2 to be a possible water world larger than Earth, but in the just right band around its sun. Kepler-45 to be nicknamed Earth's cousin. Because of its similarity to our own world, each name is a whisper from the past, a postcard from a watcher that no longer sees, and the ripples continue. Kepler paved the way for new missions. TESS, the Transiting Exoplanet Survey Satellite, which now surveys nearly the entire sky. JWST, the James Webb Space Telescope, which can peer into the atmospheres of some of Kepler's discoveries. Kepler lit the match. Others carry the flame, but none did what Kepler did: stare at a patch of sky for 4 unblinking years, seeking dimness and turning it into knowledge. There's a kind of reverence in Kepler's method. It didn't chase the bright Atida. It didn't demand attention. It waited for the absence, for what wasn't there. It trusted that truth could live in the faintest of shadows, and it was right. Now, imagine this. Somewhere in the sky, Kepler once watched, a planet continues to orbit. Maybe it has clouds, maybe oceans, maybe forests that know nothing of telescopes or Earth. But Kepler saw it just once, just a dimming, and for that moment, planet was known, acknowledged, not alone. That is the legacy, not in the hardware, now drifting cold, not even. In the discoveries though, there are many, but in the act itself of watching, listening, of waiting without knowing what might come, Kepler reminds us that patience is not passive. It is an active reach, a belief that meaning lives in quiet places. So tonight, as you close your eyes, think of that quiet satellite, once wrapped in sunlight, drifting just beyond Earth, its eye pointed toward the stars, not hoping for drama, not demanding miracles, just watching and finding a universe full of worlds. You are drifting again, far from sound, far from sunrise, far from home, a silent orbit, not around Earth, but beyond it, out past the moon's pull, to a quiet place where warmth would ruin the view. There, floating in shadow, waits something, golden, something built to look not forward, but backward, not into distance, but into time. It is not your eye, but it sees for you. This is the James Webb Space Telescope, and it has just opened its golden lids, launched on December 25th, 2021. Webb was a gift we sent into the dark, not a telescope to look at planets nearby, not one for close-by stars or casual glances. It was made for the deep, the ancient, the barely dashed there. It is the most powerful telescope humans have ever made, and yet it whispers, not because it is weak, but because its voice is too wide for words. Webb does not orbit Earth. It rests at L2, the second Lagrange point, a gravitational balance 1,000,000 miles from our planet. There, stays behind Earth as both move around the sun, always in Earth's shadow, always cold, always still. That stillness matters. Heat would blind its eyes, okay? Motion would blur its vision. Webb had to become a machine of silence, and so it did. It was a machine of folds, of secrets wrapped in gold and mylar. It launched as a compact package, then bloomed in space, petal by petal, shield by shield. Its sun shield is the size of a tennis court. Its mirrors the shape of a honeycomb. Its heart colder than Pluto. Every unfolding step had to work perfectly. There were 344 single points of failure, each one like threading a needle blindfolded in the wind while drifting through space. But it worked. Every latch, every unfurling. And when it opened its eye, the universe changed. Webb is not like Kepler, not like Hubble, not like any other. It sees in infrared, a range of light you cannot see with your eyes. Why? Because the universe is expanding, and with expansion, light stretches. Blue becomes red. Visible becomes invisible. Infrared is where the oldest light lives. First galaxies, it's the faintest stars. It is the color of beginnings, and Webb sees it all. Its mirrors are not silver, not glass, but plated with gold. Gold reflects infrared well. It is not just beauty, it is function. But still, there's something poetic about looking for the oldest light with mirrors made of treasure in its first images. Webb delivered more than beauty. It delivered time. It showed galaxies so far away that their light began its journey over 13 billion years ago. You saw galaxies as they were just 300 million years after the Big Bang. Infant galaxies, still forming, still colliding, still glowing with first stars, and you, with eyes made of carbon and water, seeing back almost to the beginning. The Webb does more than look back. It also looks into clouds of gas, where stars are born, into dust, where planets form, into atmospheres light years away. Atmospheres. Let that settle. This telescope, 1,000,000 miles from Earth, can detect the ingredients of a sky on a planet you cannot see. How? It uses transit spectroscopy. When a planet passes in front of its star, some of the starlight goes through the planet's atmosphere on its way to us. That atmosphere leaves its fingerprints in the light. Webb reads those fingerprints. It sees water, carbon dioxide, methane, ammonia, even possible clouds. From that, it begins to answer a very old question. Could life live there already? It has found water vapor on hot, giant planets. It has detected carbon-rich skies and hazes and swirling cloud tops. It is painting a picture of exoplanets, not as dots, but as places. Places with weather, places with seasons, places with chemistry, and perhaps, someday, signs of life. But Webb's power is not just in what it sees. It is in how it sees. It captures light that began its journey before Earth formed. It sees stars that lived and died before our sun was born. It can look inside stellar nurseries where baby stars are wrapped in gas. It can watch galaxies collide, watch black holes feed, watch the slow ballet of cosmic evolution. It sees not the now, but the becoming. And yet, for all its power, Webb is fragile. It cannot be serviced like Hubble was. It cannot be repaired by astronauts. It is too far. Its mission must last on faith, on engineering, on care, and so far it has. Back on Earth, golden eyes send images to a quiet team of minds and hearts and hope. Scientists wait for photons older than humanity, photons that have crossed voids wider than dreams, to land gently on a golden dish. Every image, a message in a bottle from a galaxy that no longer exists. Webb is not just a telescope. It is a time machine, a storyteller, a patient archaeologist of light. It is not loud, it is not fast, it is not dramatic, but it is profound, because in its stillness, in its gaze, it offers you a mirror. If you listen, Webb whispers that you are part of a story 13.8 billion years long, that your atoms were born in stars, that your planet is one world among many, that light never forgets, and maybe one day Webb will find it. A planet not too hot, not too cold, with air that breathes, with water that flows, and in that atmosphere, a pattern, oxygen, methane, an imbalance that can only mean something is alive. Not conclusive, not certain, but enough to wonder, enough to dream. And what would we do if that signal came? Would we send a reply? Would we weep? Would we change? Would we simply look back through golden mirrors and whisper, "We see you," tonight as your breath slows? Know this, somewhere out there, a photon that began its journey before the first forests grew on Earth is touching a telescope made by your hands. And through that gold, that stillness, that silence, a window opens, and the past becomes visible, not in noise, not in brightness, but in light that waited and now has arrived. You are floating again, no rocket, no suit, no sound, just you, suspended between stars, drifting in thought, eyes closed, heart open. You are not afraid. There is no danger here, only distance, only time, it's only quiet. And in that quiet, something waits, not a voice, not a ship, not a beacon, but a question. The same one you've carried since your kind looked up at a sky full of light. With no names, the question isn't loud. It doesn't need to be. It's older than radio. It's older than language. It's older than fear. It is the question of the alone. Are we? Every star you pass whispers a version of it. Are you the only listener? Are you the only one who asks? Are you the only one who wonders? And for now, the stars say nothing back. You've sent signals. You've built machines, okay? You've searched skies with quiet, okay? Telescopes and restless hope. You've listened for decades to silence, but even silence has shape. Even nothing leaves. Patterns, and you read them all. In 1977, the Voyager 1 probe launched. It carried music, greetings, sounds of Earth, a golden record, with hopes floating now beyond the edge of the solar wind. It is more than a machine. It is a whisper, drifting bottle in a cosmic ocean. No one has answered it, not yet, But perhaps answering isn't the point. Maybe the point was to send it, to act, not out of certainty, but out of longing, to say, even without reply, we are here, and we wonder. You wonder. 2. You wonder what it's like to stand on another world, not one made in science fiction, but a real place with gravity and sunrise and dust. You wonder if someone is doing the same right now. It's out there, breathing, thinking, looking up, and wondering. You picture them not as green beings or silver ships, but as lives, moments, instants of thought gathered like sparks in the dark. Would they understand loneliness? Would they recognize joy? Would they listen for us as we listen for them? Oh, are they too distant, not just in miles, but in mind? Astronomers speak of the great silence, the Fermi paradox. If life is common, why don't we see it? The universe is old, the stars are many. The odds suggest we shouldn't be alone, and yet we listen, and the stars don't speak. Perhaps civilizations rise, but do not last. Perhaps they never leave their own worlds, or perhaps they are listening to in a different way, on a different channel, with different senses. Or maybe we haven't waited long enough. Maybe silence is just the space before the echo. The search for life is also a search for time. We're catching brief signals in an ancient sea, looking for sparks in oceans of static. We seek biosignatures, gases like oxygen, patterns of chemicals that don't occur by chance. We scan atmospheres, we map motion, trace the subtle dimming of stars, and we hope that somewhere a world breathes, that it exhales something more than rocks, wind, and yet, even if we never find a signal, never receive a message, never hear a voice, we are still changed by the act of looking, because the search itself requires hope. It demands patience. It builds wonder, and maybe in this vast, cold dark, wonder is enough. You imagine Earth as seen from far away, not as continents or clouds, but as a tiny dot of blue hugging a small star on an ordinary arm of an ordinary galaxy. Nothing shouts from it. No bright flares, no flashing beacons, just a steady warmth, a chemistry that should not exist without breath, without life. And that's how we might look to someone else, a maybe, a perhaps, fragile question hovering in light. The SETI programs listen every day, arrays of dishes tuned to the sky, analyzing signals for patterns that might mean deliberate thought. A radio wave, a pulse, a beat that repeats in a way nature wouldn't. So far, no patterns. It's only the sky and its normal noise. And yet, the dishes remain, still turning, still scanning, still listening, because to stop listening would mean giving up the question, and we are not ready for that. Some say we should not listen, but send. We should beam our own signals across the dark. Say hello before anyone asks, but others warn. What if what listens does not wish us well? The debate is not just science, it's philosophy. Do you whisper into the unknown or wait to be heard? Do you announce your presence in the forest before you know who else is walking it? But the truth is, we've already spoken. Our radio, our TV, our radar pulses from wartime and weather reports. They've been leaking into space for almost 100 years. We are not quiet, we are not hidden, we are just small. And space is wide. If someone hears us, they may not answer for centuries. The distance is too great. Even light is slow, and the gap is measured in light years. Perhaps their message is already on the way. Perhaps we're the ancient ones, and they are just learning how to build radios. Perhaps the message will arrive when we no longer exist, and someone else will hear it, will listen, will wonder in this long silence. We have built something even more powerful than words. We have built curiosity, and that may be the first kind of contact, a resonance of thought across stars, an agreement, unspoken, that to look is to believe there is something worth seeing. Maybe this silence is not an absence, but a beginning. Maybe the universe is holding its breath, waiting for the moment when wonder reaches out and finds itself reflected. And if we are alone, then let us be kind rulers of this rare oasis. Let us treasure what we have and what we are. Let us guard this blue world as if it is the only one, because until we know otherwise, it may be, and that makes everything here more precious, more sacred. You drift again. The stars are still here. The dark is deep, the quiet is wide, but your heart is full, not with answers, not with discovery, but with something older, gentler, a question that keeps you company, a question that watches as you fall into a slow, welcoming sleep.